Dr. Chalmar? So I'm going to go quickly. Tomorrow there's a talk of all the philosophy, what's so important about a direct method. While we're changing, direct method, one reason, a very important thing in research is what problems are you looking to solve. An important property of a direct method, this is that you can figure out whether you're working on the right problem. In other words, a direct method gives you two things. One is you're solving the problem. Yes? You got the quadratic equation, you have roots, minus b plus and minus, you solve that problem. Yes? You could be guessing. If the quadratic equation was a problem today, no one would have derived minus b plus and minus. We have search algorithms, FWI kinds of things, matching, looking for roots, never finding a double root, keep looking and looking, you understand? Matching. But there's another value. There's one value that you have a problem that you decided was interesting, yes? You thought relevant. And you go and you solve it directly. Great. But how do you know from the beginning that the problem that you chose is the real problem? Well, how is the following? If you choose a problem and you have a direct solution and it does not improve your drill success rate, you have the wrong problem, because you can't blame the method. It's direct. If you have an indirect method, you get workshops. We keep on looking, You don't know it's the wrong problem, you don't know it's the wrong method, you keep on different, you understand? That is a very serious issue, yes? Because choosing what to work on is the most important issue in designing a research program, yes? So if you don't know why something fails, so with direct, if we have a direct method and it doesn't improve the drill success rate, we're working on the wrong problem. You understand? If it's indirect, could be wrong problem or the wrong method. We keep looking new search, very fast simulated annealing, whatever. Yes. Okay. So ISS tutorial. There's scattering theory is a form of perturbation theory. What it says is the following. Let's say you have a source and you have a medium. Let's say something about that medium changes, anything. A reflector moves, at one point the density is changed. Any change in the medium for the same source will result in a change in the field. Yes? There's a relationship between a change in the medium and the change in the field. Understood? That's perturbation. I change something in the medium and the field changes. Scattering theory is that relationship. The relationship between a change in the medium and a change in the field. The pointer is here. Okay. So with that talk, if this is some original medium with a differential operator L0 with some parameters in it, this is some Green's function, this is some idealized source, and then now you have L is a different, you perturb this L0 and you turned it into L by changing the properties inside of L0. And then when you did L0 into L, G0, the field, became G. V is the difference between the original and the new medium, if you like, and G minus G0 is the difference between the original field and the new one. This is an operator identity. This is a very old identity. If you want a quick derivation, in some way, L, G are inverses, because this could be looked at as a unit, a dyadic, and the Dirac delta being a spatial representation. And so in some vague way that we don't want to be too careful about, G and L are inverses. Okay, in other words, if you want G, it's like L inverse. Okay, so in the sense I just mentioned, this is L inverse, this is L0 inverse, this is L0 inverse, V is L0 minus L, and this is L inverse. And you can see that this is true because you put this and this, you get 1, you get L0 minus, cancels this, you get this and this, you get 1, and you get L inverse, matches. So this is an identity. This is also exactly the equation that we had an hour ago with P is P0 plus integral G0 plus K squared alpha P. Okay? So if that form G0 plus times rho gives you that equation. Okay? G0 plus times rho. This is due to the active source in the reference, and this is the scattered wave. Okay? G0 plus times what we call back then in a simple acoustic K squared alpha total field. Okay. So this is not controversial. If this is a concern, we have a different problem. This is an operator identity, like sine squared plus cosine squared is 1. Okay? Very old and solid. This is not a solution. You have G here, you have G here. This is a relationship. However, a very long time ago, 1920s, Born and Neumann on the math side, they made an expansion here. They said, well, let's make this G approximately, this G, make it G0, and then take this G0 plus G0 VG0 and stick that in for G. Keep doing that. You get this series like this. This is called the Born series or the Neumann series. Now you have a solution. Okay, by iterating this away, you have on one side, this is the field in the medium L. This is a modeling equation. Every modeling method, reflectivity, lattice Boltzmann, finite difference, needs the medium. This is no different. If you want to model, the field G due to the differential operator L, you need to know L. You need to know everything about L. This description here is requiring L, but in two pieces. It needs L in terms of V and L0. L0 enters as G0. Yes? So this is not a radical thought. This is modeling in terms of the medium, just term by term. This gives you the field and the reference and starts to give you some linear contribution due to the difference between the reference and the actual. A key point about this form, is, this is hard to overstate. You take L0 is an original medium. You perturb it with V. You perturb it no matter what. You can change the density at one point by 1/1,000,000 of a percent. You have a V. For any V, the difference in the field between the new field and the old field is always nonlinear in V. V squared, and so on. Yes? The simplest and most well-known form of that is the Zollpritz equation. If you have a homogeneous whole space, you have a plane wave just go straight through. You suddenly perturb it, make one below, change the elastic properties, yes? So it's no longer homogeneous everywhere, homogeneous, and then a new homogeneous. You get a reflection, a change, a G minus G0 if you like, yes? That G minus G0 is nonlinear to everything that changed. Yes? Nonlinear. Bortfeld is an approximate to that, yes? So that's the other key is this is a geometric series. This is a geometric series. This is VG0 squared, AR squared, AR cubed. Geometric. Not, it is a Taylor series, but a geometric series is a very special Taylor series. Yes, a very special Taylor series. A geometric series, there are terms when a geometric series has an inverse. In general, a Taylor series doesn't. So most of our work in inverse in the world is always thinking Taylor. So you get think D, well, we won't think with that. D of M equals D of M0 plus D prime of M0 delta M plus D double prime delta M squared over. This is the thought. This is Taylor series. A Taylor series, so that's why they stick with iterative linear. Because if you go, this doesn't have, a Taylor series doesn't have an inverse series. A geometric series does. The inverse of a geometric series is a geometric series, and that's the inverse scattering series. Okay? Okay. So just as you could write what I said, you can write that as a geometric series, where if you look at, this is AR squared. If you just think for a minute in terms of as though this was a scalar problem, you have AR over 1 minus R. In other words, the first term is AR, G0, VG0, AR squared. So the first term is AR over 1 minus R. You can take that formula and solve for R. Now you have a geometric series for R in terms of S over A. Yes? Assuming this is all arguing for plausibility, you understand? You have to go into, this is more complicated than this an algebra problem. But it lets you know what the scalar analog is. So just as just as you would have, in other words, in a you have a series S equals AR plus AR squared plus AR cubed. Understand what the difference between this and Taylor? Taylor, this would be some kind of F prime, F double prime. All of these are the same. Yeah. You understand? It's geometric is usually simpler than Taylor. The structure is so simple. That's what the forward series is, geometric, which allows an inverse. In other words, if we consider this S1, S2, S3, meaning this is the portion of S that's linear in R, the portion of S that's quadratic in R. You get a series for R from wherever that slide was, which looked like S over A minus S over A squared, and so on. This is R1. This is R2. In other words, this is the linear estimate of S. This is the quadratic S contribution to S. This is the linear contribution to R. This is the quadratic contribution to R. Okay? You're not going to iterate linear. This is the linear, this is the quadratic. You have explicit form for each order in each direction. Okay, so that's the motivation, the the scalar motivation behind the inverse scattering series. So analogous to R is V. V1, V2. V1 is the portion of V, the unknown between L0 and L, that's linear in the data. V2 is the portion of V that's quadratic in the data. And you get a, just like you have here, this is R1, this is R2, you get formulas. In fact, analytic formulas for V1, V2, as long as your reference is homogeneous. What this is saying is there are a lot of people who believe the inverse, the forward, that solving an inverse problem, you take a forward problem and you solve it in an inverse sense. And this is saying that's just a flawed thought. That is only true if the direct inverse is linear. What's an example of a direct inverse that's linear? Claerbout 3. You give me velocity, I get the image, linear in terms of the data. Yes? Source and receiver, that experiment's linear. That's why it's so close to modeling. In other words, there, the forward and the inverse, okay, are inverses of each other. The forward run backwards. Take the data back. Yes? You understand? Because once it's nonlinear, so in other words, if you have a relationship that's exact, that's linear, S equals AR, this is exact, then R equals S over A. This is exact. In other words, I can take this and run it backwards. It's the same as the inverse direct. Look what happens if it's nonlinear. S equals AR plus AR squared. Yes? Let's say that's your forward problem. Now run it backwards. You get two roots, R1 and R2. You make R3. You get three roots. You go to R to infinity. Get infinite roots solving the forward problem in an inverse sense. And guess what? There's only one root. S over A, 1 plus S over A. Look how far off you get by solving a forward problem in an inverse sense and think it's the same as a direct inverse. You get growing number of roots, yes, for higher polynomials, yes? And that's just a simple, we'll say more about that tomorrow for multi-component. Okay, we wandered off. This is the slide. This is like your S equals R1, okay? This set of equations are the equations for solving for V using the inverse scattering series. Just like you have an R1, R2, R3, R1, R2, okay? This equation requires data. G0 is water speed propagation. You have here a relationship between data and V1 and G0. You can solve for V1 here directly in terms of your data and water speed. In fact, V1 is a Stolt-Claerbout 3 migration. Analytic. There's a data, you put it in a form and you get V1, analytic result. You take that V1 and put it in here. So what is V1? V1 is close to data. This is data times data. Okay? And you get a portion of V, a contribution to V that's quadratic in the data. Again, a portion of V that's cubic in the data. Data, data squared, and so on. All you're doing here is multiplying data by data. The inverse step is always the same. What you did to invert to get V1, if you were looking for it, is what you do to get V2. The background remains G0. So if this is analytic, this is analytic, and this is analytic. The complexity comes in multiplies. That's why free surface multiple removal is data times data. That's why internal multiple is data times data times data. It's multiply. When you're going to see Q compensation without needing Q, data times data times data. Okay? It's multiplicative. So someone say, well, there's a lot of multiplies. That's true. And multiplies take compute, yes? But if you say, do I want to multiply data, or do I want to take a data and make and invert it? In other words, make a perturbation and then update. I'll multiply any data you want. Multiply, it's stable, yes? There's no step there which depends on the band-limited nature of data to find a new update, okay? So this is a great slide, except it's useless. The good news is it's clear. The bad news is this scheme, as Dr. Carvalho, the first thing in his thesis, well, I was fortunate enough to work with him, coded up the entire inverse series in 1D normal incidence with primaries and multiples, yes? And the convergence was very narrow, yes? Like only, if I remember, 11%, the difference between water speed and the earth, which is worthless. It doesn't get through the water bottom. So this wonderful scheme have no social value, okay? But that scheme says in comes data, out comes earth. So the thought was, this is the only multi-dimensional direct method. Maybe we can find subseries that achieve tasks within this and see if they are convergent and data acceptable for the data we collect. That scheme, most of the terms in this scheme do not do isolated tasks. They try to do free surface multiple and internal multiple and depth imaging, all kinds of things as well as they can at second order, at third order. There's certain terms that act certain very small fraction of the overall terms that do isolated task, only free surface, only internal, only depth imaging, only Q without Q, yes? Those isolated tasks are a small fraction. All these others are coupled tasks. We believe the coupled tasks led to that original divergence because every isolated task to date has been convergent. And we know the whole picture didn't. You understand? So you follow? Most of the terms are trying to do at fifth order, they do whatever they can to fifth order. Everything it can. I'll do a little of that. I'll do 3 orders of free surface. I'll do some depth imaging. You understand? That is what we've... So, that isolated task subseries of this, if you have a subseries, if every term here doesn't care about anything but data and G0, every piece of every term has that property. And that's simply why ISS, isolated task subseries, have been useful. So, for example, the free surface algorithm, Paulo Carvalho's free surface algorithm works 1 temporal frequency at a time. If you have a certain 9 hertz in your data, it removes multiples at 9 hertz, okay? That's very strange for an inversion, yes? As soon as you say band limited, the first step, in other words, what's going on there? We stay in data space. This is data. This is data. Where's the model space? Here, in here. The only time we go to model space is if we want model space. Like if we want parameter estimation, I got to go to model space. Haiyan Zhang, Hong Liang, yes? Everything else, free surface multiple, internal multiple, okay? Depth imaging is model space. Q without Q, not. We want data in, data out. As long as you stay in data, you are safer. The closer you stay to data, the better your algorithm. The soon as you enter model space, things get trickier, bandwidth and all the rest. Okay? Okay, so that's the logic behind the inverse scattering series and an isolated task subseries. So with that, two things have just happened. We said why, with smooth velocity modeling, multiples have to be removed. What this says is that multiple removal of both free surface and internal can occur without subsurface information. Now we're going to see the state of things, yes? Progress on the front of multiples with that background. Are there any questions? Okay. Well, is this lunchtime?